Alright, so today we are going to go through a very exciting topic. Now, here's the deal. In advanced functions, you are supposed to learn about this notion called continuity. You aren't actually interested at first in what continuity is, you're actually more interested in discontinuity, which is a little bit strange because you're introducing a concept's negative before you actually introduce the concept itself. The problem is, in order to explain what continuity means, you need another tool, and that tool is often not presented until you reach the calculus course. So the way I'm doing it is the way that makes the most logical sense, although it does introduce some more technical stuff first. So what we're going to do today is cover something called the limit, and then we're going to see what that means for this interesting idea called continuity. And throughout this, you should really think of it as a sort of brief preview of calculus. So the limit is an idea that's going to come up over and over and over again in calculus, and continuity is just one of the several topics that you'll be covering in MCV. Okay? So that's why I've titled this lecture Shades of Calculus. Alright, so let me just go and write this, draw this function. Okay, and it's just going to continue, but what I'm going to do is I'm going to put a big red box right here, and it's going to keep going. Okay, now what I'm going to ask is, what do you think could be inside that box? Of course, there are infinitely many possible things that could happen inside that box. But probably the easiest and most simplest thing that you're thinking of is just like a way of connecting this side, that side. So like build a bridge, just like that, right? Of course, some more complicated things could go in here, right? So let me expand my box, just like this. Okay, so this is the same big red box, just blown up so you can see it easier. And the function comes in from this side, and it exits out that side. Okay? So my question is, what could happen inside this big red box? And the first thing that we said was, well, you could have a very simple connection from one side to the other. You could also perhaps have like some oscillation here, right? And I mean, it is a function after all, so I mean, we've never defined the domain of this function, so we could just have nothing, you know? You could just enter this box, do absolutely nothing, and then come right back out. Okay? So, okay, that's a couple of interesting things that could happen in this box. What happens if I make the box smaller? If I make the box smaller and give you more of the function, it starts to become a little clearer what happens inside that box. Right? Of course, there are still infinitely many possibilities. Let me blow up the box again. The exact same things could happen. I could have a connection from here to here. I could have oscillations. I could just have absolutely nothing at all. I could even have a line, a break at a single point, and then a line just coming out of that. So as you can see, there's a lot of possible options. But of course, there's always like a most obvious option, right? And that is the very first one that we discussed, which is the option where you just, connect from one side to the other. If I made this box so imperceptibly small, it doesn't even show up on the camera, it would seem like there's not really much that this function could do inside that box. And that is a limit. A limit is a way of making a guess, a very good educated guess at what your function does as it approaches a point. So to make this more precise, suppose I centered my box at this point A, right? Now what I'm curious about is what value can my function approach as it gets closer and closer to A? Okay? So as x approaches A, what value can this function take on? And as I've shown you, as the box gets smaller and smaller, there are less varieties, there are less possible options. In fact, I can make my box as small as I'd like. I can make it infinitely small to the point where it's literally just a speck on the board. It's still a box, but to you, it just looks like a speck on the board. And, you know, you'd have the same thing, you know, like the most logical thing is just a connection, right? So now that I've given you sort of a rough idea of it, let's talk in more real terms, okay? Because at the end of the day, what we're trying to do is we're trying to find what value the function f can take on as it nears x equals a. Okay? All right. So remember, a is a point on the x-axis, and what we're trying to find is a y value, a coordinate. Right? And just the way I've drawn it, you know, that seems to be a valid candidate for the coordinate. Of course, like I mentioned, a bunch of random things could happen inside that box, but this seems to be like the most valid candidate. And it seems to be the most valid candidate because just by your intuition, you're approaching that value. Your function is approaching that value. So this value here gets a very special name. Okay? This value here is called, we'll call it L. And here's our definition, our very loose definition. I actually haven't said anything precisely so far. But our rough definition is L is the limit of the function f as x approaches a. Okay? X approaches a, we will abbreviate as x arrow a. That just means x is going to a. And this whole thing here, we are going to, instead of writing this, we're going to use the more compact notation. And this is the actual notation that you need to know. Okay? It's lim for limit. You have to declare what function you're talking about. And you say that x is going to a. Okay? And this doesn't make any sense. We have to give it a value. So we'll give it the value L. Okay? Understand what this statement is saying. It's saying that as x approaches a, right, it appears that the function is approaching a value. And that value is the value we call L, and that we define to be the limit of the function as x approaches a. 2 points need to be made here. 2 points. So the first point is, we need to have that both sides of a agree, right? So both sides of f around a must agree for L to exist. Okay? That's our first caveat. The second caveat is that f of x need not exist at a. And this might seem very strange to you. So in other words, f of a might be undefined. Now this might seem very strange to you because in your head you might be thinking, well, doesn't that kind of defeat the purpose of the question? Because were we not trying to like figure out what this function was approaching? You know, isn't that the whole point of this limit thing? And the answer is no. The answer is no. If I wanted to know what the function was doing at a, all I had to do was evaluate it at a. But I've specifically hashed the problem into this very strange way. I've turned it into a problem that approaches. So I'm not concerned with what the function does at a. I'm concerned about its approach to a. Okay? This is a very crucial point. Because what it means is that at the end of the day, if I make my box super, super, super small, I don't actually care what goes on in my box. All I care about is the y value that this function seems to be approaching as I enter the mysterious box. Okay? So let me just keep this on the board and make some very important distinctions using some examples. Okay, so the first example that I'm going to use, we're going to use a good old function, just y equals x, okay, or f of x equals x. Okay, very simple function, and we're going to just go through some things about this function. All right, so here's my function y equals x. Okay, and what I'm going to do is I'm going to ask what is the limit as x approaches 1 of this function, x. Okay, well, it's very evident. You just look at it and say that, oh, the function as it approaches 1 is approaching, well, what is that? Well, the function is f of x equals x, and it's just 1, right? So 1. Okay, the quick way of doing it is just taking 1 and putting it in there. That worked this time. Okay, very important to note, that worked this time. Might not work every time. What do I mean by that? Well, let's see. Okay, here's another example. I'm going to replace x and just change it very slightly. Okay, all I'm going to do is replace it by this function. X times x minus 1 all over x minus 1. Okay, I want you to go and graph this function to see why I even bother doing this. Okay, but when you graph it, you'll notice something is very peculiar. It differs from x, f of x equals x in only one way, and that one way is this. You may be even able to see it just by looking at the definition of the function. It's that at x equals 1, right? So at x equals 1, the function does not exist. The rest of the function looks like x, and maybe you could see that if you just, cross the x minus 1 and the x minus 1, but at 1, the function doesn't exist. There's like a little hole. Then what is the answer to our problem? We can't actually do that. We can't actually plug in 1 into here, because if we put a 1 into here, I mean, that's a calculator error. That's going to be 0 over 0. What is that? Okay? However, looking at the graph, right? Remember, we're not concerned about what the function does at 1. We're concerned about the approach. And as we travel along the function, going closer and closer to x equals 1, right? The y value gets closer and closer to 1. So that's the answer. The limit is the same. The limit of this new function, x times x minus 1 over x minus 1, is still 1. Okay? That might be a little difficult to wrap your head around at first, but as you get closer and closer to it, you'll really begin to identify spiritually with the idea that the limit is not about evaluating, it's about approach. We're concerned about approaching the value of f as x gets closer and closer to 1. Okay? Once that becomes clear, all of these limit problems are going to turn into very, very, very easy. Just look at the graph and spit out the answer. Okay? So those were the two examples that were really important to go through. And in these, I illustrated both of these principles. Both sides of f need to agree around a, and f of x does not actually have to exist at a in order for the limit to be to exist. Now, let's get some examples that violate principle 1. Okay. So, let's violate principle 1. I'm going to draw a graph. Okay. And I'm not going to tell you the function this time because this is going to be a piecewise function. Okay. So let's do sorry, let me just do it in a different color. So let's get a function f that does this. Okay. And then over here, it takes on this point, and then it jumps over here and does something like that. Okay. This is going to be the point 1, right? Here, let's call this -2, and let's call this 2. Okay. Now, here's the question. What is the limit as x approaches 1 of f of x? Okay. Notation-wise, what that means again is that we want to know what value f of x approaches as x gets closer and closer to 1, right? That's what the x arrow 1 means, okay? But look at it. If I approach from this side, right, it looks like the function is going to send me to 2 by the time I get to 1. And if I approach from this side, it looks like my function is going to send me to -2 by the time I get to x equals 1. And of course that violates principle 1, right? So look what it says. Both sides of f of x around a must agree for L to exist. Here they disagree because the right side is trying to say, oh, I think I'm going to reach 2. Whereas the left side is trying to say, no, I'm going to reach -2 by the time I reach x equals 1. Of course, the reason why they are disagreeing is because of this gap, this gigantic gap that I've drawn here. Okay? So, in this case, we actually have to say something special. We have to say the limit does not exist. Okay? The limit does not exist. Let me show you another example. Okay? Here, let's just get our good old rational function 1 over x. Okay? The first thing you'll tell me is, of course, the point that I want to look at is x equals 0. And as if the first example wasn't obvious enough, obviously the limit here doesn't exist. But let's just think about why it doesn't exist. Because it's not really because of the same reason that you might think. Okay, so we're going to look at the limit as x approaches 0 now of f of x, which is going to be 1 over x. And of course the limit does not exist. You can see that one side is going to infinity and the other side is going to negative infinity. There's no way it could possibly exist because both sides of f of x, they must agree. But there's an even bigger issue. Even if they did agree, the limit would still not exist. Okay? And this is a very strange phenomenon. Well, let me just illustrate it by changing this function slightly to 1 over x squared. You can check on Desmos right now, just pause the video and check, that 1 over x squared is a function that looks like that. Okay? So let me just put a square here. And I'm going to tell you that, again, the limit does not exist. And you'll say, no, just wait. Look, at x equals 0, this side is going to infinity, and this side is also going to infinity, so they must agree, right? They both agree at infinity. That would work, except that L, remember, was a number. Infinity is not a number, right? A number, remember, this goes back to our very first lecture, a real number has to be something that lies on the real line. If I can't give you the real line and you can't point at it, it's not a real number. Infinity is not a real number. Therefore, we can write just to like indicate to our viewer that, you know, the limit is technically infinity, but really what that means is that it doesn't exist. Because, like, there's no number. There's no number that f approaches as x goes to 0, because infinity is not a number. Okay? So that is another very important principle. So let me just recap on the side what we have said. I think what I'm going to do is I'm going to just cut the video here and just rearrange everything. So just bear with me for a sec. All right. Okay, so I've just thrown everything that we had, all of our observations and findings on the left side of the board. And we're just going to continue looking through some more examples. And these are really just pictorial. In calculus, we're going to go through the limit more in depth. We're going to solve some very difficult limit problems. In fact, we're going to be able to solve limits without even looking at a graph. That sounds incredibly difficult, but in the end, after you're done advanced functions, you would have technically been prepared for everything that you need to do in order to solve these limits without an image. For the purposes of introducing the limit as an idea right now, I just need you to get the intuition behind the idea and identify when a limit does not exist, and also when a limit does exist. Those two ideas are what we are trying to get for in order to explain continuity. Okay? So let's just go through one more example. And the example that I want to go through with is one where all sorts of things are happening. Okay? So here's my axes. Okay? I'm going to do this. Okay? So this side looks like it's 1 over x. Okay? Now we're going to do this. A break. All right. Okay. So let's get started. I'm going to ask 3 questions, and I think, I'm going to ask 5 questions, and I think 2 of them you should be able to solve just based on what we have done so far. So I want the limit here at 0, I want the limit at 1, I want the limit at 2, and I want the limit also at infinity, and I also want the limit at infinity. Okay? Negative infinity. Okay? Now, you might be just completely overwhelmed right now. Which one can I solve? Which one can I not solve? Well, let me give you the answer. These 2 you should be able to solve right now. Actually, these three you should be able to solve right now. They're just combinations of these, right? So if I give you numbers like this is 1, this is 2, this is 3, you should be able to solve the following. Limit as x approaches 0 of f, limit as x approaches 1 of f, and limit as x approaches 2 of f. Get used to writing this notation. You're going to be doing it a lot. Okay? I'd actually recommend that you just write these 3 down on a sheet of paper right now and just try and pump in some answers. Okay? So pause the video, put your answers, and make sure our answers line up. So here, in the first case, it's infinity, but really the answer is it doesn't exist. Here, it does not exist. The reason being because as x approaches 1, the 2 sides of the function don't agree. The approach is not similar, right? This guy says, I'm approaching 3, and this guy says, no, I'm approaching 1. The one confusion you might have is, well, as I'm approaching 1, don't I run into some trouble here? Or as I'm approaching 1, don't I run into some trouble here? Well, the answer is no. You just have to pick a small enough neighborhood of 1 in order to perform this operation, right? We're only concerned about the approach to 1. We don't care about anything that happened before. We don't care about anything that happened after. We only care about as you approach 1, okay? And as far as we're concerned, the approach to 1 looks like it's getting closer and closer to y equals 1. And the approach to 1 on this side looks like it's getting closer and closer to y equals 3. Okay? This one, the limit is 2. Okay? The reason being because it doesn't matter that f of x doesn't exist there, right? All we're concerned about is the approach. On both sides, the approach agrees. Both sides say, oh, I'm approaching 2 as x approaches 2. So the limit as x approaches 2 of f of x is equal to 2. Okay? So the last 2 questions, and these are the last things that we really need to be concerned with, are these. Limit as x approaches negative infinity, and limit as x approaches infinity. Now you may be protesting right now, hold on, you just said a moment ago that infinity was not a number. How come you get to write infinity here and here? Well, it's because this notation indicates approach, right? Just because infinity is not a real number doesn't mean I can't approach it. Doesn't mean I can't get closer to it. Okay? So infinity and negative infinity, those are concepts, okay? But it still makes sense for us to discuss about what happens as x becomes really, really, really negative and what happens as x becomes really, really, really positive. In fact, a lot of practical applications of math are concerned with these 2 questions. What happens way, way, way down in the future? Or what happened way, way, way back in the past? You know, you may have seen in grade 11 functions, you get these questions about exponential growth or exponential decay. And, you know, they kind of look like this, right? And here what's going on is that you see, well, oh, as as time goes on, the amount of stuff becomes really, really, really small. How do you make that precise? Well, this is the tool. Okay, this is the tool that you use to be able to say that, oh, this function looks like it's approaching nothing as time goes further and further. Okay, so going back to our example, let's just answer these two questions really quickly. The first one is the harder one, so let's just look at that. As x approaches negative infinity, I should have just drawn like a dotted line here. So the dotted line represents that this function will never touch the dotted line. It will get closer and closer and closer, but it will never touch it. And so in this case, this dotted line is situated at y equals 0. So all that means is that as x approaches negative infinity, it's going to get closer and closer to 0. Right? Now, another question you might be having. Over here, I said both sides of f of x around x equals a must agree. This is clearly not applicable here, because what is to the left of negative infinity? Like, there's literally nothing. Negative infinity is like as far left as you could possibly go. So when we're considering these two special cases, I'll just box it up. Okay, these are different. Rule 1 does not need to apply because there's literally nothing around negative infinity. There's nothing to the left of negative infinity. There's nothing to the right of infinity. So our answer here is actually 0. And our answer here, you may have guessed already, is infinity. Except remember, infinity is not a number. So we have to say, like, you can put it in quotation marks. I'm putting it in quotation marks. But really the answer is that it does not exist. The infinity is just there as a notational convenience. Okay? Alright, so hopefully this example was enough to give you the rough idea of what a limit is, and hopefully now you have some intuition about it. There's only one thing that should be really concerning you, is that in the original examples, it looked like, you know, you could just do this, right? When we were dealing with y equals x, right, it looked really easy. Like all you had to do was plug in 1 into the equation. But later I showed you an example where you couldn't do that, and where in fact that would lead you to nothing, right? So this leads into the next discussion, which is continuity. There is a case where you don't actually need to look at the graph. You just can get the function, and if you want to know the limit, you just plug in the number, right? So to give you an idea of this, let's take another function. We'll call this a special function for now. And our special function is, of course, x squared. We're looking at y equals, wow, that's a gigantic negative axis. We're looking at y equals negative x squared, and I want to find limit as x approaches 1 of x squared. Actually, let's make it more interesting. Let's do 2. Okay. So, what is this going to be? Well, 2 is like somewhere here, right? And we know that, you know, if you do 2 squared, you get 4. So just right off the bat, you should be able to say 4, right? Because, you know, you just look at the picture. Both sides agree. Nothing goes wrong. Well, you're absolutely right. However, you did this only because this function did not have anything nasty going on. And what we mean by nasty is exactly the things that we had were problems in here. Those are called discontinuities. Okay? And this is why they're taught first instead of continuities, because continuities require limits to fully understand. So it's this notion of discontinuity that we're going to be approaching now. Alright. So let's just talk about how a function can be intuitively discontinuous. Okay? There are 3 cases, and we've actually seen all 3 already, but I'm just going to make them explicit in each of the following diagrams. Okay? And they all have names. So this is called infinite. This is called jump. And this is called removable. Okay? So an infinite discontinuity, as the name implies, is something like that. Okay? So in this case we have a infinite discontinuity at x equals 0. I'm going to do x equals 0. I'm going to do the discontinuity at x equals 0 for all of these examples. Now an infinite discontinuity, it can look like this, but it can also potentially look like this, right? So if both sides go to infinity, that's also a discontinuity, and the reason why it's a discontinuity is because it just straight up isn't there, okay? It isn't, like, it's not even there. A jump discontinuity, it usually looks like this. Now this one can take on several forms, but the main idea is that there's a gap, right? So as your function approaches from the left, it does not agree with what the function is doing as it approaches the right. There's like a gap, and that is a discontinuity at x equals 0. Okay? You can just like visually see it's a discontinuity because the function breaks. That's your intuition for discontinuity. It breaks. Okay? The removable discontinuity is perhaps the most subtle one, and it looks like this. Okay? Now the thing with a removable discontinuity is that as long as you filled in that point, the function would be continuous. Okay? It's still a discontinuity because the function is not existing at that point. It's a break. However, it's very clear what point you need to fill in order for this function to be continuous again. So that's what we call removable, because it's like you just took a point and just removed it. Okay? It's not as severe as these two. Typically, these two discontinuities are very severe. This one, sometimes it's even difficult to tell that there is a discontinuity just by looking at the function. But I'm going to show you how to tell right now. Okay? So here are some facts. Okay? So facts. When you have a function that has denominator 0 for some value of x, let's call it a, there will be a discontinuity. Okay? And there are only two types that can arise from this. Namely, you can only get infinite and removable. Now I want you to graph on Desmos the following functions just to be able to see this, okay? The functions I'm going to give you are very similar to each other visually. As functions they look very similar, but on the graph they look completely different. Okay, so the first function is x plus 2 over x minus 1. And the next one is x squared minus 1 over x minus 1. Okay? So go ahead and take a look at these two functions. You'll notice that this one has an infinite discontinuity at x equals 0. Right? So if this paragraph over here was a little confusing, all I'm saying is if f has a denominator 0, when I replace x with some number, then there will be a discontinuity at that number. So in this case, when I put x equals 1, that means that there will be a discontinuity at 1. And similarly, over here, when x equals 1, the denominator will be 0. So we know there will be a discontinuity there. Okay. The question is, how do you know whether your discontinuity is infinite or removable? This example actually contains all the information that you need. Okay? So the fact is, with removable discontinuities, if you notice this top one, you can factor it. You can factor it as, and let me just write it over here. So we write it as x squared minus 1 over x minus 1. This is x plus 1 over x minus 1 over x minus 1. So you might be able to look at this and say, oh, these two cancel, right? So I'm just left with x plus 1. So what this is saying, what does this mean? F of x looks like the function x plus 1, except there is a removable discontinuity. At the point x equals 1. Okay? So that's how you interpret these removable discontinuities. When you get things that are canceling in the function, they create removable discontinuities. Because you can never really get rid of the problem that the denominator created. If you stick a 1 in here, you will get 0 over 0. That's a problem, right? However, it doesn't mean that you can't factor it, so that the rest of the function looks pretty much exactly like x plus 1. The only problem part is going to be at x equals 1. Okay? So that's how you tell whether there is a removable discontinuity or an infinite discontinuity. All you have to do is look at whether you can cancel anything on the top and the bottom. Okay? And if you can cancel something on the bottom, then that discontinuity is not infinite anymore, it becomes removable. Otherwise, all the discontinuities are infinite. Okay? So, there's only one last question. Okay? And our last question is just, how can you get a jump discontinuity? And here's another fact. Unless you're presented with some very, very strange function, only piecewise functions can jump. Okay? So that doesn't mean that piecewise functions can only jump. It means that the only way you can have a jump discontinuity is if you have a piecewise function. Let me reiterate that. Just because you have a piecewise function doesn't mean there is a jump. Okay? The only thing that you have to be concerned with is that your answer should never be a jump discontinuity unless you know that your function is piecewise. I mean, just visually, like look at it, right? Of course there has to be two pieces that define this function in order for there to be a jump. None of the functions that you've dealt with so far, and none of the functions that you will deal with in this course, other than the piecewise ones, will have breaks like this naturally. Like, just think about it. Trig, your exponentials, your polynomials, your linear quadratics, none of them have jumps. Okay? Some of them might look like this, like your rational functions, and I've just shown you an example that looks like this, but these ones you can only get if you have a piecewise function. Okay? So let's do a couple of examples. Of course, this little fact here means that most of the examples that you're going to be given are in fact piecewise. Okay? So that's bad news because it means that you have to decide between all the three. It's not going to be simple like this. Alright, so my first example is, let's see, I want to do x squared minus 1 over x plus 1, x minus 2. Just something easy to start us off. Okay. You should be immediately able to see that you can factor the top, like so. Okay, x plus 1 and x plus 1 cancel out, and I'm just left with x minus 1 over x minus 2. Now I should not forget that at the beginning here, there are some restrictions. For example, x cannot be equal to -1, and x cannot be equal to 2. All I've done here is that I removed this pair, this canceling pair. Okay? So what does that mean? Well, this is not a piecewise function, so we know that our only possibilities are infinite and jumps. And removables. Okay? And according to the facts and classifications that I gave you earlier, it should be clear that we only have one infinite discontinuity and one removable discontinuity. The removable discontinuity is at x equals -1, and the infinite discontinuity is at x equals 2. Okay? So that's a first simple example. It kind of follows the same pattern that we had before. You can graph this, just make sure, graph the top one, not the bottom one. Graph the top one just to make sure that, it all makes sense. All right, let's do one that is similar but tricky. Trickier, not tricky, it's trickier. Okay. All right. So let's do x squared plus 9 times 2x squared minus 17x minus 9 over 2x plus 1 x minus 3 x plus 2. Okay. Now eventually you're going to get to the point where actually this whole thing is multiplied together. You can see that it's going to make a degree 3 polynomial in the bottom. It's going to be gross. Similarly, this one up here, if you multiplied it all out, it would be some degree 4 polynomial and it would be horrendous. We're actually going to work to that, to the point where you should be able to break down these gigantic polynomials into a factored form. That might sound a little daunting, but once you've got the procedure down, it's actually not that hard. We're actually going to start doing that next week. Okay, so let's see. None of these you can break down, right? They're all in their lowest form. Let's just go ahead and say which x values are forbidden. Okay, so we know immediately right off the bat, just by looking at each of these, that x cannot be negative 1/2, right? If you want, you can just solve 2x plus 1 equals 0, right? We don't want this thing to be 0. If you solve for x, you just get x equals negative 1/2. Okay. We also can't let x equal to 3, and we also can't let x equal to negative 2. Okay. Now, the only question is, does anything up here cancel? Okay. And here's the trick. Actually, sorry, I wrote the question down wrong. My bad. All right, so now that we fixed up the question, we can continue on and see if there's anything that we can cancel. The first thing I see is this thing here is the difference of squares. Like I said, difference of squares is the prime trick for trying to fool grade 12 students because it's so simple but so easy to forget. Okay. Now the last question we have is this one. What can you do with that? Okay. So take a minute, try and factor it on your own. This is a good exercise in reviewing. And I believe you get, let me just check. I believe it's 2x plus 1 times x minus 9. Yeah, that's right. Okay. All right, so that's what you should be getting. If you just look carefully, you can cancel out two things. This one and this one. Okay, and you're left with x plus 3, x minus 9, all that over x plus 2. Okay, so the only thing that's left here is an x equals to minus 2. So now we can classify our discontinuities as infinite or removable. And of course, our infinite discontinuity is at negative 2, and our removable discontinuities are at negative 1/2 and 3. Again, you can graph this gigantic thing just to make sure that we're right, but that's the answer that you should be getting. Okay? Alright, so we've done enough of those. Actually, maybe we've even done too many of those, because this is sort of going into what we're going to be doing in rationals. But it's good to get a little bit of practice just knowing what kind of discontinuities can be created by what kinds of functions. Now we're going to go into something more difficult, which is the piecewise case. Right? So I'm going to show you how to tackle the piecewise case. Alright, so here's my first piecewise function. It's going to be 5x plus 2 and negative 2x plus 9. Okay, so how are we going to tackle this? Oh, sorry, I should put x is greater than 1, x is less than negative 1. Okay, so how are we going to tackle this? This is kind of daunting. So here's a fact. We only need to worry about x equals 1. That's the only value that you need to worry about. The reason why is because everything after 1 looks like the function 5x plus 2. And just from your grade 9 knowledge, you know that 2 is a line. And a line is continuous. There's no gaps or breaks in a line. It doesn't just go off to infinity somewhere, right? It eventually reaches infinity as x approaches infinity, but the function itself will never actually touch infinity. So this part is not a problem. So we don't need to care about x is greater than 1. In the exact same way, we don't need to care about x is less than negative 1. X is less than 1. The only thing that might be a problem is at x equals 1. So just to give you like a schematic, what we're worried about is the following. Okay, so here's x equals 1. Let me just draw this side in red, and let me draw the other side in purple. Okay, so negative 2x plus 9 is going to look like what? Okay, so here's 9, and it's going to look like what? That, right? Something like that, right? What we're worried about is that the other function, 5x plus 2, it looks like that. Okay? So the dotted line means that we're not considering that anymore, right? So really our function is just the purple, the solid purple, and then it jumps to the solid red, right? The little dotted lines just indicate that the line continues, right? If it weren't a piecewise function. Right? So this is just how you graph it. So this is our worry. Our worry is that this function jumps at x equals 1. However, we know for sure that everything before 1 is fine, and everything after 1 is also fine. So again, x equals 1 is the only part that we need to worry about. How can we determine whether this function is continuous at x equals 1? All we have to do is take the limit of this function from both sides. Okay. Now, to do that, what can you do? Well, here's the thing. You know that this function here, in red, is 5x plus 2. And you know that this function, in purple, is negative 2x plus 9. And you know that they're both continuous. They are lines. How could they not be continuous? A line is always continuous. It's like connected all the way through. Okay? So what you can do is just think about what does the value of negative 2x plus 9 take on at x equals 1. So if I just plug in a 1 in there, what do I get? Okay, let's write like this. Limit, as x approaches 1, of negative 2x plus 9. Okay. Now, because negative 2x plus 9 we know is a continuous function, we're not going to run into any problems. So we can just literally substitute in a 1 here, and we'll get negative 2 plus 9 is 7. Okay. Now, the red one will do the exact same thing. Try it yourself. Okay. Of course, because 5x plus 2 is a line, it's continuous, so I can just sub in 1. And that also gives me 7. So what does that mean? What does this result mean? Well, it means that as these functions approach 1, as both these functions approach 1, they both approach the value 7. So our image here is a little off, isn't it? Let's redraw it more accurately. Okay. So accurately, what this image should look like is the following. So here we have 9, here's 2, and 7's like up here or something. Okay. So negative 2x plus 9 is going to look something like this. Okay. And let's let this here be equal to x equals 1. And we know that at 1, our function, negative 2x plus 9, is going to hit 7. And we know our red function is going to also hit 7. It's 5x plus 2, so it's going to look like that. Okay? So that's what our piecewise function looks like. And just by looking at the image that we've drawn now, this new image, it's continuous. You didn't have to draw this image, you could just look at this. Right? You could just look at this and say, well, look, they both approach the same value as x gets closer and closer to 1. So we know that it must be continuous. Okay? Because everything to the left of 1 is continuous, everything to the right of 1 is continuous, and at 1, we know that you can like smoothly go from one to the other because they approach the same value. Okay? Now, and of course it's important that f is actually defined at 1, which is why I have the equal sign here. So it is equal to 7, this thing approaches 7, so we're fine. Okay? This illustrates the important fact. This illustrates the important fact that I'm going to write above. And we're going to use this actually to solve the next problem a little bit faster. Which is that the function f of x is continuous. And in the future for continuous, I'll write CTS for continuous at x equals a if and only if limit as x approaches a of f of x is equal to f of a. Okay? So that might be a little confusing at first, but we're going to go through an example now that's going to demonstrate how this might work and how this might not work. Okay? So here's the next example, f of x is equal to... And if this is getting a little bit difficult, don't worry too much. Just understand the basic idea of what continuity means, because that's all I'm going to ask you at this point. I'm just going to ask you whether functions are continuous or discontinuous. Sometimes I'll let you graph it, sometimes I won't. Sometimes I'll just give you the graph, sometimes I won't. The big takeaway is that limits are a really useful tool for being able to understand how continuity works. We're going to explore them later in the next course, but for now, the only limit that I expect you to be able to solve is just by looking at a picture. You should be able to tell me what a limit is. Okay. So, let's take on this problem, and this I think is going to be the last thing we do today. Let me just check the time. Alright. Yeah. So, let's see. Okay, we have x squared minus 4 for x is greater than 2. Okay, that's good because this is a quadratic, and we know quadratics are smooth. This is a line. X is equal to a line, so we know that it's smooth as well. It's like continuous. And x cubed is, well, it's a cubic, right? Like, you know, x cubed looks kind of like that. So it's also continuous. So that means the only trouble spots are x equals 0 and x equals 2. Again, these are like the transition points. Okay? And again, our big worry is that maybe they're discontinuous at those spots. Maybe our function looks like this. Okay? So we have x between 0 and 2. And I don't expect you to draw this picture at all. Just understand what I'm doing right now, and that's probably enough. X squared minus 4, oh, I don't know, maybe it looks like, I don't know, maybe it looks like that, you know, maybe like there's a big jump, right? And then our other worry is that maybe at this point, you know, it looks like that. Maybe that's what x cubed looks like, I don't know. So we're going to check whether this diagram is accurate. Right, so first let's check x equals 0. So our first check is x equals 0. Right? What we need to check is if limit as x approaches a of f of x is equal to f of a. If this is not true, then it's not continuous. Okay? So we should fill in some blanks here. What is f of a? Well, what is a in the first place? A is 0. We want to check if f is continuous at 0. So we'll check f of 0 first. Oh, f of 0 is, according to this rule, it's just 0, because 0 is in this range, 0 to 2, with the equal signs. And then I just apply the rule x, but x was 0, so I just get 0. Right? So this is equal to 0. Right? So our next problem is, what is the limit as x approaches 0 of f of x? Okay. Now, remember, for a limit to exist, the two sides must agree. Let's just check whether this limit exists. So to the right of 0, right, so here's 0, to the right of 0, this whole region is like the function x. And to the left of 0, this whole function is the function x cubed. And we need to check that x cubed and x agree as they approach 0. Okay? You can do this just by graphing it. They are not very difficult functions to graph. X looks like this, and x cubed looks like that. Like it literally, both of them literally are 0 at 0. Okay? So we have that the limit does exist, and just by looking at the function, looking at the graph, so remember our function is piecewise, it looks like this. Right? It looks like that. As we approach 0, both of these approach the same value, 0. And so we get 0 equals 0. The condition is true. So that means we're actually continuous at x equals 0. Okay. So now we've just verified that x equals 0 is not a problem spot. So we're going to erase it. The only thing left to check is x equals 2. So let's check that. Again, we have 2 here. On the right side of 2, it's the function x squared minus 4. On the left side of 2, it's the function x. And we're worried that maybe they're not continuous. So let's just write down our criteria again, which is on the top here. So limit as x approaches. Now a is equal to 2, right? We're worried about 2. So we'll check f of x is equal to f of 2. What is f of 2? Well, we have to look at this one because 2 is here, right? But this function just spits out 2. So we are worried that this is not equal to 2. Okay? So let's work through this. So we need to evaluate this thing, right? Again, we could draw a picture. Okay. But the picture sometimes is not going to help, so maybe we're going to try it without a picture right now. Okay? So in order for this limit to exist, again, remember, both sides must agree. What is on the left, on the right of 2? It's x squared minus 4. Alright? So let's just figure out what happens as x squared minus 4 approaches 2. Okay? Well, because x squared minus 4 is continuous, it's smooth, what you can do is you can just plug in a 2, right? You know, x squared minus 4 is a parabola, and all you need to know is that, let's see. Well, actually, you can just look at it and know that if you plug in a 2 into here, you'll get 0, right? So that means that x squared minus 4 is approaching 0. Okay, as we approach 2. But the function x, as x approaches 2, well, this one's really easy. It just approaches 2, right? And clearly those don't match up. So because they don't match up, the limit doesn't exist, and therefore there's no way that this piecewise function could equal to the limit could equal 2 because it doesn't exist. If it doesn't exist, then it can't equal to something. So we have at x equals 2 a discontinuity. Okay. So at x equals 2, f of x is discontinuous. Okay. So in this lecture, we went a little bit above and beyond what you would normally do in advanced functions. However, this is definitely something that will pop up once again in MCV, and I think it's a good idea that you get a bit of a feel for it. Don't worry too much about being able to do all the calculations. Worry more instead about understanding intuitively what it means for a function to be continuous, okay? Because that's the things that are going to be tested in advanced functions. I just think it's improper if you're just left with an intuition and that's about it, and then you're forced to go through the rest of this course not actually knowing what continuity is. This right here is continuity. Your intuition that, you know, the function never like detaches is literally this thing in math form. Okay? So just keep that in mind. We're going to be discussing a little bit about continuity as we go through the course, so that's why I wanted to bring it up here. But more importantly, we're gonna see next lecture what happens when I literally force continuity. I can do things to functions that will force discontinuity to happen. Okay? So we're gonna see that next time.